The focus of this lesson is continuity. In calculus, we will define a function f as continuous at a if the following conditions are met. Number 1, f of a must be defined. That is, a is in the domain of our function f. Number 2, the limit of f of x as x approaches a must exist. That is, the limit from the right and the limit from the left must exist. And then number 3, the limit of f of x as x approaches a must be f of a. And if these 3 conditions are met, we say that a function is continuous. Now, looking at the graph here, we see that this shows all 3 conditions. We can see that our function f is defined at a by looking at this red point here. We can see that the limit exists, that as we approach a from the right and from the left, we approach the same f of a value. And we can see that this value matches where the function is defined. Example 1. The graph of a function f is shown in the figure below. Use the graph to determine whether the function is continuous at the values 1, 3, and 5. Now, let's start with 1. So if we look at 1, which is right here, we can see that, unfortunately, our first condition is not met. So we can say that at 1, our function is not continuous because, well, f of 1 is undefined. Thus, our function f of x is not continuous at x equals 1. Now let's take a look at our next point, at 3. Now at 3, we can see that in fact our function is defined, and f of 3 is -1. However, so we see that f of 3 is defined, and it is in fact -1. However, when looking at the limit, we can see that if we approach 3 from the right, we're at 2. Whereas if we approach it from the left, we're at -1. So we can then thus say that the limit of f of x as x approaches 3 does not exist. And it doesn't exist because the limit of f of x as x approaches 3 from the right does not equal the limit of f of x as x approaches 3 from the left. So f of x is not continuous at x equals 3. Now let's look at our last one, at 5. At 5, we can see that the function is in fact defined. We can see that f of 5 is 3, therefore it is defined. We have a value. We can also see that if we approach 5 from the left, we're at 1. If we approach, from the right, we're at 1, and from the left, we're at 1. So we can see that definitely the limit of f of x as x approaches 5 is in fact 1, but our third condition is not met. The third condition being that the limit of f of x as x approaches 5 must be our defined value. So since f of 5 does not equal our limit of f of x as x approaches 5, f of x is not continuous. At 5. So all 3 of these are examples of cases where we have discontinuity. All right, let's take a look at example 2. Determine whether each function is continuous at the given value. So remember, we must check three conditions. Is the function defined? Does the limit exist? And is the defined value the same as the limit? Now, immediately, when I look here, I see that 2 is not in the domain. If I plug in 2, I get a divide by 0 error. So since f of 2 is not defined, we're going to say that this function is not continuous. So f of x is not continuous at 2. Now on b, g of x. So let's check once again. So this function does in fact define specifically a value for 0. So that helps us some here, because the first part of the piecewise function, plugging in a 0, would create a domain error. So we do know that g of 0 is defined. G of 0 here is in fact 1. Now remember, our next condition is that the limit must exist. So let's go ahead and let's check. So the limit of g of x as x approaches 0, say from the left, is, let's say, the limit as x approaches 0 from the left of 1 over x squared is 1 over, and we're starting from the left, so we're dividing by a really small negative, like a negative 0.00001. If I take a constant 1 and divide by a really small negative, we're going to go to negative infinity. And if I do the same, but from the right, I have the limit as x approaches 0 from the right of 1 over x squared, which becomes 1 divided by a really small positive, which is positive infinity. Therefore, we can see in this case that the limit does not exist. So the limit of g of x as x approaches 0 does not exist. Therefore, g of x is not continuous at 0. Let's take a look at h of x. So this function looks very similar to the one we just saw. So we have here 2 is the value we're checking for continuity. If we were to plug it into the first part of our piecewise function, we could see that it does not work. Therefore, they have defined h of x as being 1. So it is in fact defined. h of 2 is 1, is defined. And then let's check our limit. So the limit as x approaches 2 from the left for our h of x is going to be the limit as x approaches 2 from the left of our function, our piecewise function, which in this case, I'm going to go ahead and just factor it, is x minus 2 times x plus 1. And do note that's just this numerator here, factored out, over x minus 2. And the awesome thing about that is we can see that those factors cancel each other, leaving me with the limit as x approaches 2 from the left of x plus 1. And then simply doing our direct substitution, we're going to get 2 plus 1, or 3. Now, at this point, I can go ahead and stop because the value I'm getting here is 3. And even if I check from the right, and I also get 3, which I will, the problem is here is that our function is defined of h of 2 being 1, and this here is 3, and they do not match. So we can see that the limit as x approaches 2 does not equal h of 2. So we're going to say that h of x is not continuous at x equals 2. All right, now let's check g of x, which is our greatest integer function. Now remember, the way this function works is it whatever number goes in, it gives the greatest integer that is less than the value that goes in. So remember, if we plug in, say, pi, out comes 3. If we plug in 7.5, out comes 7, etc. So first off, let's just check g of 3. So we can see here, g of 3 is our greatest integer of 3, which is just 3. Now let's check our limits. So the limit as x approaches 3 from the left of g of x is the limit as x approaches 3 of our greatest integer function from the left. And then we're just going to plug in a number to the left of 3. So like a 2.999 essentially. So out will come a 2. And then the limit of g of x as x approaches 3 from the right. And we have the limit as x approaches 3 from the right of our greatest integer function. And if you remember correctly, if we go from the right, so like a 3.001, it will spit out 0. Now, because of both of these conditions, we can see that the limit of g of x as x approaches 3 does not exist. And therefore, g of x is not continuous at x equals 3. All right, there are multiple types of discontinuities. The first of which is a removable discontinuity. Removable discontinuities are those that can be removed by filling a hole by redefining f at x equals a. So in situations like here, where you can factor and cancel out that domain issue, you get a hole. And whenever you have a hole, you can simply redefine this value and say, redefine it by shifting it. So in this case, I could change this to a 3 and define it in such a way that removes the discontinuity. Whereas here we have what is called an infinite discontinuity or a non-removable discontinuity. There's no value for f of a that would make this function continuous because the hole here is an asymptote and not a single point. Then we have what are called jump discontinuities. These occur when the graph of the function jumps from one value to the next without taking on any values in between. So you see here, like these stairs, these are all jump discontinuities, and these cannot be removed or filled. All right, we're going to say that a function f is continuous from the right at a if the limit of f of x as x approaches a from the right is f of a. Or we could say that a function is continuous from the left at a if the limit of f of x as x approaches a from the left is defined at f of a. So it is possible that it's not fully continuous, but it's just continuous from either the left or the right. So let's take a look at this greatest integer function one more time. Is it continuous from the right or from the left? So let's take a look. So let's play with x approaching some value a from the left of our greatest integer function. And let's assume a can be any value. So if I plug in a, right, what it's going to spit out, and this is a number left of a, it's going to spit out a number that is 1 less than a. So for example, if it were 3 and we're less than 3, like a 2.99, it would be less than that. Okay? Whereas if I were to come at it from the right and plug in a number to the right of a, so let's say this were 3, and I were to plug in 3.5, it would come out simply a. Now, the question is, now if we're assuming that a is an integer, because those are the places where we have the steps, then f of a of our greatest integer function will spit out a itself. So from the right produces our